is really hard to think about having another one.
Okay, let's get started here. So test number 1 is on Wednesday. We'll spend about maybe about the last half of class, maybe 30 minutes discussing the test. We will spend the first part of class then continuing this data distributions correlation section. Are there any questions before we get going here? Okay. Let's see now. We left off, I think what might be about page 139 in your notes. Maybe 141. Sorry, or not 141. I changed the numbering in my notes from when I originally printed this off. It might be DDC 41. Is that something like that? Okay, so last time we spent part of class talking about the multivariate normal distribution. And one of the reasons why we talk about the multivariate normal distribution is because some of our statistical methods that we're going to be talking about in this class, the mathematical statistical theory, the underlying part that's the underlying mathematical and statistical theory for these statistical methods often have a multivariate normal distribution assumption associated with it. So you might be wondering then, if you have a sample, how can you determine if it comes from a population characterized from a multivariate normal distribution? Well, why would you want to do that? Well, if it isn't, and your underlying statistical method or underlying statistical theory for a method relies on that assumption, maybe your method's not going to work as you had expected. So, for example, you might find a confidence interval for some quantity. Let's say it's a 95% confidence interval. Well, the true confidence level might not be 95%, might be 80%, might be 70%, or even lower, because you have violated some of the underlying statistical assumptions, let's say, behind a particular method. So that's why it's important to think about, well, how could you determine if a sample actually comes from a population characterized by a multivariate normal? Unfortunately, though, it's not an easy thing to do. Where did that go? There it is. So in your first stat course, when you're talking about, let's say, univariate data, let's say you have one variable, you have a random sample, what would you do? What would be like one of the first things that you would do to make a judgment of, did this data come from a, let's say, univariate normal distribution? Well, what kind of plot?
Histogram.
Yeah, histogram. So you might do something like this, and hopefully, it looks something like this. Not the best drawer in the world, but notice how it's mound shaped, kind of symmetric, and probably what you would do too is that you just kind of eyeball it here, kind of fit a line to that shape that you see here, and that kind of looks like a normal distribution. Okay, so essentially what this line that we just drew in is you could say f of x hat, essentially, because it's basically estimating what the true univariate normal distribution, f of x, would be. Okay? Well, what happens now then when you have two variables? And you want to know if a bivariate normal distribution, if the data can be characterized by a bivariate normal distribution. How would you check the multivariate, how would you check the bivariate normal distribution assumption in that case with the sample? We talked about one way last time. Do a contour plot? Yeah, and then what else? What else would you do with this contour plot? Just a contour plot itself? Anybody want to help out? All you have to do is go back, I think, 1 page, 2 pages in your notes. Remember doing something like this last time? Where we had a sample, we plotted the sample in a scatter plot, essentially on top of the contour plot. If it looks like the sample kind of elliptical in shape, then I suggest, well, yeah, bivariate normal distribution looks appropriate for that data. What could be another way that you could examine for a bivariate situation? What do you think would be another way that one could assess bivariate normality? Think what we just did with this particular plot here.
3D plot.
A 3D plot, yes, but what kind of 3D plot?
Surface.
Well, what are you drawing the surface on? That? Well, what is that? A frequency distribution, yeah. Okay. It's a histogram. But now we have two variables. So what kind of histogram would it be? Essentially a 3D histogram. And then, just like how I drew on here, you could put a surface on the top of those 3D bars. And if it looks kind of like what we've seen from 3D plots of actual multivariate normal, bivariate normal distributions, then you might think, okay, yeah, that bivariate normal distribution stuff's going to work out for your particular sample. Is everyone clear on that? Okay. Well, what happens now if you have three variables? How could you check trivariate normality if you have a sample? How could you check to see if trivariate normality works out? Just call it a day and say, can't do it.
A two-way combination.
In what way?
Well, if you have variables A, B, and C, you can do A, B plot, B, C plot, A, C plot.
In terms of scatter plots?
The three-dimensional
Yeah, you could do the 3D histograms for all pairwise combinations, but all that's assessing is essentially bivariate normality, not trivariate. And that's just because you have, let's say, normality between, let's say, x1 and x2, x1 and x3, and x2 and x3 does not mean that you have trivariate between all three of them.
But if any one of those fails, you know you don't have.
Yes, that is correct. Yeah. So, I'll actually kind of get to that for an ad hoc way for checking multivariate normality, is you could use something like that. But let's say if we did really want to check trivariate normality, though, how could we do it? So imagine a scatter plot in 3D of x1, x2, and x3. What shape do you think the points would fill in that three-dimensional area if you did truly have trivariate normality? What shape do you think? Essentially what you would have is you could do, now let's think of the extension of a contour plot in 2 dimensions to 3 dimensions. So imagine that this football here is, let's say, f of x is equal to 0.01. Okay? And essentially what you can think of is that your points from your sample would fill up inside this football. And you could have, let's say, a bigger football around this. Let's say f of x is equal to 0.001. So imagine now another surface around there as well. And you can see some points, not a whole lot of points, but some points between this football and this outer football as well. So you could actually do a 3-dimensional contour plot, and essentially you would have these what are called ellipsoids. That would be the contours, where f of x equal to 0.01, 0.001, and so on. So you could do a plot like that. I feel like I'm a Nebraska football player. I just fumbled the ball. So you could do a plot like that. But what happens now if you have more than 3 variables? Now you get problems. Okay? And it's kind of a shame because, again, many of the statistical methods that we've talked about in this class, that we will talk about in this class, are dependent upon this multivariate normal distribution. But we really, when you have a lot of variables, you really don't have a good way to assess normality. And similar to what was mentioned before, what you could do is approach it in an ad hoc manner, you could say. This will not guarantee that you do have multivariate normality, but it seems like a good thing to do with the lack of anything else better to do. And that is, let's say, to do all possible pairwise scatter plots of your data. So let's say x1 versus x2, x1 versus x3, x1 versus x4, x2 versus x3, and so on. And if in these scatter plots that you plot, if it seems like the points are forming similar to what we saw above here, kind of an ellipsoid kind of shape, or ellipse kind of shape, I should say, then okay, it looks like maybe multivariate normality holds. If it doesn't follow this shape, then you know, okay, you got a problem. So that will be one way to approach it. Was there a question? Okay, sorry. Let's look a little bit closer at this bivariate situation. If you remember, we looked at this particular example, or this particular normal distribution last time. And here's a plot of what that normal distribution looks like through this surface. And let's say that we have a sample, and we want to see if this sample essentially kind of follows this shape that we see in the true distribution itself. So, similar to what we did, or as I mentioned here, if you had a univariate situation, you could draw a histogram and essentially, put this little normal distribution curve on it, and that's your, let's say, f of x hat. It's an estimate of f of x. Well, we can do this in a lot more formal manner through using statistical methods called kernel density estimation to do this for other, more than one dimension, you could say. And so what I did here, I'm going to skip ahead a little bit, show you the plots, and then describe how I got these plots. What I did here is I took a sample size 2,000, and through using this thing called kernel density estimation, I found f of x hat and plotted it. Let me actually go to the actual plot here so I can rotate it, and we can see, in comparison to that green surface that we just saw a few minutes ago, for the actual true bivariate normal distribution, you can see how, yeah, it looks like the same kind of shape. Well, of course, this would be expected if I'm actually taking my sample from a population characterized by that bivariate normal. That's what I did, in case I didn't say that. So this is for n equal 2,000. What do you think would happen if I lowered my sample size to maybe 200? Would you expect it to look closer to the actual green surface that we saw up here? Or would you expect it to maybe look a little bit more different? More different, perhaps. I've given you the answer already in the notes. That's why you didn't want to speak up. And in fact, it does look a little bit more different. Let me just run this code real fast. Again, I'll explain it to you shortly. And we can see, here's now for a sample size of 200, you can see what's happening. Now look at it, it looks like you're even getting like another mode, you could say, if you think of it in 3 dimensions, another mode to your distribution there, and it's not looking as good as it did before with a larger sample size. And we could go one step further and take a look at a sample size of 20. Ooh, look at that. So if somebody gave you that, would you say, yeah, that looks like that sample comes from a multivariate or a bivariate normal? Well, probably not. You have those 2 peaks there. But we do know in this particular case, the sample is coming from a bivariate normal. So one of my purposes of illustrating this is that normality can be very hard to assess. Even when you know you have underlying normal distribution. Okay? Let's talk about how I got this plot. Okay, so similar to what we did last time, I'm going to set a mean vector, a covariance matrix. I'm going to set my sample, let's say, to the size of 20. I'm going to set a seed so I can reproduce my results. We talked about the RMV norm function last time. That's what actually is going to simulate my data. And so if I run that, here's my sample size of 20 from this bivariate normal distribution. Now, to actually create this f of x hat, again, I'm going to use something called kernel density estimation. I think kernel density estimation's the actual underlying stat part to this method. I think it's better discussed in some other class than a multivariate course. We're just using this simply as a tool to help us visualize something, not necessarily understanding why this particular method works, how it works, or variations of it. So because of that, all you're responsible for is to how to actually implement this in R. There's a function called KDE2D, kernel density estimation, 2 dimensions. It's in a package called MASS. That stands for Modern Applied Statistics with S. There's actually a famous book by that name that talks about how to use R and also S+. And simply the way that this function works is that you put in your first variable for the x argument, put in your second variable for the y argument. What you get out then in this fx.hat, you get 3 things. A whole bunch of, essentially for us, x1 values, x2 values, and then a matrix that contains all of your f of x hat values, which would go on, let's say, the z-axis of your plot. And similar to what we did last time, we use this Perspec 3D function to actually do the plot. Simply how it works. Let's actually do a 2000 again. So here's 2000 once again. Oops. And if you really wanted to make this kind of, I don't know, maybe cool looking, is that you could actually plot the original original bivariate normal distribution on the same plot by using exactly the same function that we did. And then I say add equal true to actually add then the actual bivariate normal distribution to the plot. And this is what we get. And you can see how they are roughly very similar in the shape, as you can see there. Are there any questions? So, again, assessing multivariate normality is a hard thing to do. We have some ad hoc measures that allow us to do it for as many variables as we want. But again, it's a hard thing to do. Yes? Sure.
One of the things we did in univariate statistics was to look at the mean and the median and whether they approximated each other. Is that something we would do in multivariate statistics?
I mean, you could do that. I don't think it's going to be that much more of a help than doing, let's say, a scatter plot. Scatter plot probably tell you more than just simply looking at mean and median. And for those of you who are wondering, why would you look at a mean or median? It's because the mean and the median are the same for a univariate normal distribution. And it's essentially, but here's the problem. Defining the median in 2 dimensions or higher is not as easy to do. So I take that back. That it will be a little bit more difficult to do. Okay? Yes.
So in a maybe journal context where you're going to use a method that assumes normality, would you just say we assume normality based on visual inspection or something like that?
You would say we assume multivariate normality, and you say, well, to get a rough assessment, let's say maybe you choose a different word than rough, to get a rough assessment, we examine pairwise scatter plots of the data and seem to everything fall into like an ellipse-like shape. So that's what you do. Other questions? Okay, let's move on. Let's now talk about, move that split. Standardizing data. I think all of you have done this in some context before. So this is kind of just making sure that you understand it and what we're going to be doing in this class. So in your very first stat course, and I think they were actually doing this in Stat 801 before we came in here today, they were finding, they were saying, let's let x be distributed normal mu sigma squared, and then how could I transform this to a standard normal distribution? Well, you do this nice little transformation here. X minus mu divided by sigma is distributed normal 0, 1. So essentially by dividing by the mean, by subtracting off the mean, you're basically centering your random variable. Now it's centered at 0 versus mu. Divide by sigma, now you get a standard deviation of 1. Okay? So that's in the context of a normal distribution. But instead, if you really wanted to, if you just simply said, you have a random variable, a random variable that has a mean and some kind of standard deviation, and if you want to transform it to a random variable as a mean of 0 and standard deviation of 1, you could do a similar transformation. Now, with your actual sample itself, let's say if you want your sample, your particular variable that you have in your sample, suppose you want that to have essentially a sample mean of 0, a sample standard deviation of 1. Well, what would you do? Well, that's what we have here. You know, some people might call this a z-score, for example, in a class that you've had before, where you take your x. Remember, in our notation, r represents the observation number, j represents the actual variable. So for the rth observation, jth variable, you subtract off mu hats of j. In other words, the sample mean for variable j, divide by then the square root of the estimated variance for that jth variable. We're going to call this z sub rj. We could put all these z's into a matrix. Remember, we had this x matrix, this data matrix that we had before. We can put this all into a matrix of z's instead and call that matrix z. Now, why would you want to standardize data? Do I have the answer there? Yes, I do, unfortunately. Why would you want to standardize data? Well, often you have, and especially in our cases, we're talking about multivariate statistics. We're going to have multivariate data, and we have, you know, maybe p different variables, and each can be measured on a different scale. So it can be hard to make comparisons from one variable to the next. And in fact, in some of the statistical methods that we'll be looking at, it's going to be essential for us to standardize stuff. Otherwise, you get totally, let's say, poor results. Because let's say, for example, let's say you have a particular variable that is measured in, let's say, hundreds, 100, 150, 200, 300. And then you have another variable that's measured 0.1, 0.2, 0.3. Well, which variable is going to have a larger variance? The variable that's measured in the hundreds or the variable that's measured in, let's say, like 0.1, 0.2? Well, the variable that's measured in the hundreds. Some of the statistical methods that we're going to be looking at focus on that variance. And they're going to see, oh, this variable has a very high variance, so I'm going to focus on this variable versus this other variable that has a smaller variance. You'll see that, for example, when we talk about something called principal component analysis. And so that's why oftentimes we want to standardize our data first before we approach doing various statistical methods. So how can we do this in R? It's not too difficult. Here's the serial data. I'm going to work with the sugar, fat, and sodium variables. These have been adjusted for the serving size, as we've done before. To standardize your data, simply, you can use the scale function. So say scale, the variables of interest, and I put the results into an object called Z, and there's the first 6 standardized observations. And just as a reminder, essentially what R is doing is going back to its original, let's say, X matrix, or it's going to, I guess, columns 8 through 10 of the serial data frame, and it's finding the mean for each column, it's finding the standard deviation for each column, taking the original data value, subtract off the mean, divide by the standard deviation. I demonstrate that process right here for the sugar variable. So in this particular case, I just pull sugar out of cereal. I find the mean sugar value, and I divide by the standard deviation. What do I have left in the end? I have a variable that now has a mean of approximately 0. It's 10 to the negative 16th power, so that's why that's approximately 0. And then I have a standard deviation. So yes, indeed, I did standardize. This scale function does work. Or, I'm sorry. Yeah. No, actually, I didn't check that. I'm sorry. Let me do that again. Oh, yeah, I printed off. You see the variance there. I tell you what, for homework, you can verify that indeed that the mean for these sugar values is 0 after you have standardized. I did? Oh, okay. Sorry. Yeah. Thank you for pointing that out. Obviously, I need to look closer. One thing I find hard about teaching in the mornings is that, at least for me, when I teach, I have to basically go through the entire lecture in my head before class. And so that means I do prep for about an hour and a half before every single class that I teach that go through the lecture. Well, you know, when you have a 9 o'clock in the morning class, that means I would at least have to start by 7:30. Now, it's going to be rough to do that in the morning, especially when you have 2 little kids, 1-year-old and 4-year-old, that you're trying to get ready to go, and they don't want to get their clothes on today. Anyway, so that means I have to go through it at night. And so, you know, between going through it at night, I was up till about 10:30 last night going through this. From going through it at night, sleeping, and now doing this, I forgot that, yes, indeed, I did put the mean there, and also, obviously, you have the variance. Anyway, okay. Well, now I want to emphasize a few things here that you may or may not have seen before in your first stat course when you dealt with standardizing data. And that is, here's my covariance matrix for Z. Okay, for this Z matrix. So for example, here is the estimated covariance of Z1 and Z2 if 1 was sugar, 2 was fat. Okay, it's 0.239. Let's look at the correlation matrix using the core function that we looked at last time. So if I call this, let's say, R sub, let's say Z1 and Z2, look at, they're exactly the same. Why does that happen? Yeah, remember how you find a correlation. You take a covariance divided by the square root of the 2 variances. Well, if your variance is 1 for each of their variables, guess what? The correlation is equal to the covariance. So that's why that happens. Also, something else that interesting that happens, I'm going to just flip back here to page 35 real quick. Do a split screen with that. There we go. So back on page 35, what we saw was the correlation matrix for the unstandardized data. And look at how that matches the correlation matrix for the standardized data. They're the same. Why does that happen? There's a few different ways you could answer that question. Why does that happen? The correlation, let's say, is a unitless measure. It's a unitless measure. Hopefully you learned that in your first stat course. It's always between -1 and 1. And it doesn't matter what units you're measuring in. The closer to the 1, the stronger the correlation. The closer to the -1, the closer to the stronger the negative correlation. Closer to 0, the more less related the 2 variables are. It's a unitless measure. But, you know, one could go even a little bit further and look at it from this perspective. So let's say I want to look at the correlation between Z1 and Z2. Remember, that's the covariance of z1 and z2 divided by the square root of the variance of z1, square root variance of z2. As we just discussed here, these variances are equal to 1, so I'm left with the covariance. Well, what is z1 and z2? Let's actually plug those in there. It's essentially x1 minus mu1 over sigma 1, 1, x2 minus mu2 over sigma 2, 2. Now what we learned about, I think it was last time, or maybe it was class before that, these sigmas are constants. So what I can do is I can actually pull these out, sigma 1, 1, sigma 1, 2. And then what happens to the mu1 and mu2 there? Well, how about we approach it this way? What's the variance of a constant? 0. So mu1 and mu2 play no role at all. So then I'm left with the covariance of x1 and x2, which essentially, or is, I should say, a correlation between, oh, I cannot write. Let me get my right toolbar out. No, that's not the toolbar. There we go. What we have here now is the formula, as we've seen before, for, come on, yeah, do that, the correlation for x1 and x2. That's why you see this happen. So what this means and why this is important for us is this. If I want to, if my statistical method that I'm looking at relies heavily on the correlation matrix, in fact, this is what's going to happen when we talk about principal component analysis, even factor analysis coming up. If my statistical method relies on knowing the correlation matrix between x1 and x2, I can get equivalent results from working with the standardized data. Okay? That's why that's going to be important for us later on. But for now, you just need to understand this aspect here. The correlation matrix will always be the same whether you're working with unstandardized or standardized data. Any questions? Okay. So in terms of what's fair game for test number 1, this is going to end the stuff with test number 1. We still have a little bit more to go here with this data distribution and correlation section, but this will not be on test number 1. Okay. So let's talk about eigenvalues, eigenvectors, and an interesting relationship with the multivariate normal distribution. So let's let lambda 1 be the largest eigenvalue from your covariance matrix. Let's let lambda 2 be the second largest eigenvalue, and so on. Now, these eigenvalues and eigenvectors have an interesting relationship with the multivariate normal. I'm going to state it first and then explain it. Let's look at the first eigenvector, meaning the eigenvector that corresponds to lambda 1. We saw in the matrix algebra section of this course how you could actually simply plot an eigenvector. Just so you can just think in 2 dimensions. Okay? You could actually plot then the eigenvector. Well, that eigenvector is going to point in the direction of, remember those contours that we were seeing with the bivariate normal on those plots? It's going to point in the direction of what's called the major axis of this contour for a bivariate normal. So for example, let me just jump ahead to this example here, and then I'll explain it more later how I got these plots. Here's the same normal distribution that we've looked at before. I've drawn just 2 contours, just 2. And if I were to come up with the eigenvalues from sigma, the corresponding eigenvectors, and I plotted the first eigenvector, notice how that points towards what's called the major axis of an ellipse. Hopefully, like in your algebra class, like in high school, you learn about you have a major axis, you have a minor axis for an ellipse. Simply, there's the major axis, here's the minor axis, Kind of makes sense. If you turn your head, you can see how you can see the x and y axes just simply like tilted, you could say. Then for the second eigenvalue, if I find the corresponding eigenvector and I plot it, notice how it's also pointing out in the direction of the minor axis of this contour, of this ellipse. So it's kind of interesting that that happens. Now, when you do some of this stuff on your own and you look at this closer, don't be alarmed if you saw something like this for your first eigenvector. Because remember, eigenvectors are not unique. I can simply multiply by a negative number this eigenvector and reverse the eigenvector pointing to the other direction. Okay? I think there's like an example in the homework like that. Okay. So that's kind of interesting that that happens. Also, there's one other thing I need to point out too. Sorry. Notice how with this first eigenvector, it's pointing in the direction of the largest variability. Again, if you could turn your head and, can't draw that in the middle. If you turn your head and think of like a new XY coordinate system, such like this. So this could be, let's say, how about we call this C1 in C2. So instead of plotting X1 and X2, we have C1 and C2. If you tilt your head there a little bit, you can see that the largest amount of variability is in the C1 direction. The smallest amount of variability is in the C2 direction. The first eigenvector always points in the direction of the largest variability. The second eigenvector then will point to the direction of the lesser amount of variability. Again, that's for a bivariate. We'll discuss very shortly what happens when you have a trivariate or higher dimension normal distribution. So let's take a look at some code here. So again, sorry I jumped ahead there. This is that same bivariate normal distribution that we were looking at before. And what I want to do is plot some eigenvectors corresponding to it with a length of 10. So, I've done a plot like this very similarly before. I set my mean, I set my covariance matrix. Then I'm going to come up with a whole bunch of x1 values from 10 to 25 by 0.1, x2 values in a similar manner. I'm going to use the expand.grid function, and what that does, it creates all possible combinations of x1 and x2. I use my dmv norm function to evaluate f of x. Remember, the d there stands for density. Density, multivariate, normal. I rearrange the stuff in this eval.fx in a way so that my my contour plot can be drawn correctly. So I use the matrix function to do that. And then I use my contour function as I've done before. Notice how I've purposely done a plot type of square. I want everything to be on exactly, I want the x and y axis to be on exactly the same length from the same, and also the same limits as well. So I say contour, x1 axis, I'm sorry, the x-axis, the y-axis, the contours are going to correspond to f of x. I purposely plot, or purposely state levels. What that's going to allow me to do is state, well, which f of x, which contours do I want on my plot? Just to make things look nice for this plot, I've only chose 2 different levels. And then I'm going to put a horizontal line and a vertical line. Oops, that didn't work. Let's try the whole thing again. Okay, yeah, I'm sorry, these are the grid lines, and I'm going to plot some lines at essentially x equals 0, y equals 0 on my plot. So there we go. Now, what we saw with the matrix algebra section is how do I plot actual vectors on a plot? I can use the arrows function. First of all, though, I need to find the eigenvectors. So, if you remember, there was a function called eigen that allow me to find the eigenvalues and the vectors. So let's take a look at the eigenvectors. So essentially I want to plot this first vector with a length of 10. All I have to do is multiply each component by 10. I use the arrows function to do the plotting. I'm going to start at the origin. Here's my 10 times the first element of the first eigenvector, second element of the second eigenvector, and there's my eigenvector. And I can do a similar thing for then the second one as well. So it's not too difficult. Kind of just combining two things that we talked about before, contour plot and drawing vectors on the plot. Okay, well let's look at now a situation where my covariance matrix changes a little bit. Suppose I have a lot less variability in X2. So previously, I had a variance of 1.25. How about I drop that to 0.26? So now I have 0.26. Now, if you remember with the multivariate normal distribution, we need the determinant of your covariance matrix to be greater than 0. And in this case, that is the case. Just barely greater than 0. It is greater than 0. I can find my first eigenvalue, the second eigenvalue as well, using methods that we've discussed before. I can find my eigenvectors too, although I don't show that here. Notice the correlation that we have between x1 and x2. Quite high, 0.98. Here's the contour plot. Exact same contours as before. Wow, they're a lot more condensed now. So again, where would you expect if you actually take a sample from a population characterized by this bivariate normal? Where would you expect your sample to fall? Like right here? Right? I can plot then the eigenvectors, and I guess this is a particular case where if I don't multiply by a negative number, notice how they're kind of pointing in the opposite direction, but again, I can simply point them that way by multiplying by a negative number and point them that way. And they still point in the corresponding major and minor axis for the ellipse. But then here comes the big point and why we want to even think about this stuff. So let's say that I draw a new XY axis system. We'll call this C1 and C2. So where is most of my variability? Is it in the C1 or C2 direction? The C1 direction. In fact, there's very little variability for C2. So perhaps what I could do is, if you think in terms of your data, find some kind of linear combination of your original variables. Let's say C1 is equal to, what letter do I want to use? We'll just say beta 1 times x1 plus beta 2 times x2. Suppose you find some kind of transformation like this. And we'll do another transformation for C2. So that now I can think of this, now my data in this new C1 and C2 coordinate system. If I knew what C1 is, do you think it would be worthwhile to know what C2 is? Is C2 really adding anything to my knowledge about my data on this new coordinate system? Well, let me ask you this. Do a new plot. Suppose we just have a regular old XY scatter plot. We have x1 here and x2 here. And let's say that I have my data that looks like this. So I take a sample. This is what my data is. If I knew what x1 is, somehow you knew what x1 is x2 giving you much information about your data? No, because there's very, very little information, very little variability. So if I only knew what x1 was, good, great. I understand my data then. I don't really need to know what x2 is because it's not really changing much. It has very small variability. Well, now I'll apply that same concept now to just a different axis system. If I know what C1 is, big deal. I don't need to know what C2 is. Big deal. That's the main point here. That when you see something like this, instead of looking at two variables, you can look at one variable. Just transform your variables in a certain way. We'll learn how to make this transformation later in the course. Now let's also relate this to something that you might think is helpful too. If I have a correlation of 0.98 between two variables, that says that they're closely related. I mean, what happens with x1, a similar thing is going to happen with x2. So essentially, if you had some kind of nice little equation that allow you to relate x1 to x2, well, then you could just maybe just take x1, take this equation, and you're done. You don't need to know what x2 is because you're going to have a very good idea of what x2 will be because of this high correlation. These are the kinds of things that we want to look at because it's going to allow us to simplify our multivariate data problems. Also notice in this particular situation that what's important too is that notice how this eigenvalue is close to 0. Again, when we do something called principal component analysis, that's going to be very important to us. The closer that these eigenvalues get to 0, the more likely we're going to have a situation like this. And we will only be concerned about the non-zero eigenvalues. It's going to tell us something about our data. Okay. So let's go to page 51. Okay. Let's talk about trivariate normal distribution again. Now, as we talked about earlier, you could represent, let's say, the contours by an ellipsoid for a trivariate normal distribution. You can think of the f of x equal 0.01 contour as this football, somewhere in a three-dimensional space. Okay? Now, you could find the covariance matrix. Let's say you have the covariance matrix. You could find the first eigenvalue, the second eigenvalue, the third eigenvalue. Which direction in this football do you think the first eigenvector will point towards? This part right here, because that's the longest. Just like what we saw with the ellipse in the two-dimensional case. Now, in terms of then the second eigenvector and the third eigenvector, what do you think? They're the same size. So one will be pointing, like, let's say right here, and one will be pointing this, corresponding to the seams of the football. Maybe that's what I should say. Okay? So again, the first eigenvector will be pointing towards the axis, you could say, where there's the most variability. Sorry, I lost my train of thought here. So this is actually, this football right here corresponds to the third case in this little table, where, let's say, lambda 1 is greater than lambda 2 and lambda 3. Lambda 1 and lambda 2 are going to be exactly the same, and they're going to be greater than 0. Again, think back to that bivariate case. See why that's true. Now, let's say if I remove a little bit of air from this football, what's going to happen? Well, now the eigenvalues are no longer going to be, for lambda 2 and lambda 3, are no longer going to be exactly the same. Let's say I remove all the air from this football, if I could crunch this down, and so that you basically only have this in 2 dimensions. What do you think lambda 3 will be? 0. And we're going to see the equivalent then to what we saw there for the bivariate case, where we lose essentially 1 dimension. Let's say that lambda 1, lambda 2, and lambda 3 were exactly the same. Then, fortunately, I think my wife threw out my Nerf ball that I would have for this demonstration, and instead I had to use my 1-year-old son's ball. He says, ball, 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 ball. He knows what the word ball is. Sometimes he even put this in his mouth too, but I'm not going to do that for you today. But anyway, so if all my lambdas were exactly the same, think of this as a perfect sphere. I know it's not perfect. If all my lambdas were the same, then I would have this as my ellipsoid in space that will be my f of x, let's say. And let's say if one of the lambdas was equal to 0, what would happen is that if I could press this all the way down, you would have something that looks like this, where essentially now all you need is 2 dimensions to have an understanding of what the surface would be. Now let's say that lambda 2 and lambda 3 were equal to 0. What would happen to this ball? If I could just crunch this down totally, it would be like a single small point in space. You basically lose 2 of the dimensions, and you would just have 1, essentially. So anyway, so let's extend this now to the p-variate case. So maybe I have 20 variables in a data set, and you want to have a better understanding of what the data looks like. But let's say that you find maybe the estimated covariance matrix instead, and you find the eigenvalues. And only about 2 or 3 of them were not equal to, or were not very, very close to 0. What that says to you then is that you could get as much information from looking at, let's say, a 2 to 3 dimensional representation of your data, just as much information you would get from that versus if you were to actually use, let's say, look at all 20 variables at once. For exactly the same reasons that we saw with the bivariate normal and also the trivariate normal. So because of that, we're going to be focusing often on these eigenvalues to tell us essentially what's maybe the true dimension of the data. Okay, I went a little bit longer there than I wanted to. Sorry about that. Are there any questions before we talk about the exam? Yes.
So in the page 15, that when the correlation is very high, so that you can just want to do some research on C1 rather than C2 or C2 rather than C1. But we also said the variation of C1 is greater than C2. So which variable would?
Did you say page 50?
Yeah.
Okay, so the variation of C1 is greater than the variation of C2.
Yeah. But you said the correlation between these 2 variables are very high, it's close to 1. So either one is okay to do some research.
The correlation between x1 and x2 is very high.
Yeah.
Okay. What you will learn later is that the correlation between C1 and C2 is 0. Okay? That's why you focus just essentially on C1. Okay. So let's talk about the exam. So obviously, we're going to start at 9 a.m., but I know it takes a while for the class before us to get out of here. So if you want, you can stay until 10:25 to complete the exam, because we might not be able to start right at 9, because they like to hang out sometimes. Or it might take you a while to get everything set up so that you can get started on the exam. So you got 10 extra minutes if you want it. You can stay until 10:25. Please remember that there is a formula sheet that is on my graded materials webpage. This contains our function code and also various equations, formulas that we've looked at. You can look at, it's a PDF file, you can look at that as much as you want during the exam. If you've had me for another class in the past, what I've done is actually pass out a paper copy of it. I'm not going to pass out a paper copy of it. You can look at it, that's available on my website. Okay? As for the sections that you're responsible for this test, the Intro to R, the matrix algebra, and then the data, distributions, correlation section, up until right before we get to the eigenvalues and eigenvector stuff. Now, I could obviously still ask you questions about eigenvalues and eigenvectors because that was part of the matrix algebra section, but I will not necessarily ask you, well, this first eigenvector, what direction is it going to point in with relation to the major axis of one of these contours? And we'll ask you to make that relationship there. I could ask you to draw, here's a covariance matrix, draw the eigenvector on the plot. The test itself will be 100 points possible. Again, it's 5% of your overall grade, but the test itself has 100 points. I still have to make some small changes to it because I had expected that we would have actually completed the stuff that we did today. I would have expected that we would have completed it last time, and so I took some of this eigenvalue, eigenvector with the multivariate normal stuff. I took that off the exam, and I have to replace it with some other problems. But this is the way it looks right now. It won't be too much different. Number one's worth 26 points. I'm going to give you a data set. And you're going to have to do some R calculations. And there's going to be something dealing with a regression model. Number two is worth 34 points and deals with the multivariate normal distribution. And lastly, number three is worth 40 points. And it's basically 6 short answer questions that they're not necessarily connected in any way. So I could ask you to tell me, well, explain to me what an R package is, for example. Or am I actually asking you something like find the determinant of a 2x2 matrix by hand? Okay. And there is a fourth problem that is 3 points extra credit. Okay, let's talk about the, yes.
Are you talking about training individually?
No. And I was just going to get to that. I started doing these computer-based tests, I think in 2006. And I did originally, at that time, have students turn in things electronically. What I found was some students were better at, let's say, using Word than other students. And because of that, the students who were not good at using Word to turn something in electronically, it took them a very, very, very long time to do the test. So everything's going to be on a piece of paper. So at the beginning of class, what I will do is pass out a paper copy of the exam. This is where you need to write all your answers on. Okay? And that will be the only thing that you need to turn in to me. If the problem requires the use of R, simply use the computer that's in front of you. Think of the computer in front of you almost as like a calculator that you might have used, let's say, in other classes. So you write maybe a few lines of code, get a numerical answer, put it on your piece of paper. Put that answer in. But you need to go one step further than that. You need to somehow show me your work. Just like in any kind of, let's say, a math or stat course, you need to show your work. Because let's say I asked you to find, let's say maybe an inverse of a matrix, and you totally get it wrong. And all you did was simply put down on the piece of paper that matrix. Well, how do I assign you partial prior wrong? I can't. I have no idea, most likely, I will have no idea what you did wrong. So you need to give me a little bit of more information about how you did your calculation. There's a few ways you can do that. First of all, you can write down the actual mathematical equation or formula that was used to do some kind of calculation that was actually done in R. So, for example, let's say, let's say you had to do an inverse of a 2x2 matrix. You can give me a little bit of information about how you actually would actually do the actual calculation. So there's going to be an equation on the formula sheet that shows how to do that calculation. So you can go through a few very small steps to do that. Also, you could also provide a little bit of our code on your exam. Now, I do not want to see 10 lines of code that you've written down, because then if you did that for every single problem, you're not going to finish. But for example, if you told me, okay, I entered my matrix like this, I used the solve function to find my inverse. Okay. If you somehow, for some reason, got the wrong numerical answer, I can still give you some good partial credit, because you understood the process of how to do it. Just something small probably went wrong when you were actually implementing the process in R. Are there any questions about that? So you always, for every problem, need to show me your work in some way. Even if you are 99.9999% confident that you got the right answer, show me your work.
So are you going to be, if rather, say we were finding the inverse of the 2x2 matrix, would you expect us to show both the handwritten kind of summary of the method as well as the R code?
I think a key is, well, you don't necessarily need to show both. I think it also comes down to one of those things, do you have time? If you have time, you could probably show more work, and that will be fine. But you need to show me one or the other in some way. And it's for your benefit to do that, because otherwise it's, again, hard for me to assign partial credit as needed. Yes?
We'll have access to all those on the website.
Yes, and that's something I was going to get to too, so thank you for bringing that up. I don't want you to have to memorize code for the exam. I mean, hopefully, through working through the stuff that we've done in the lecture notes, through working through the homework, through maybe doing other examples on your own, you have a general sense already. Okay, how do I find an inverse for a function? Oh yeah, it's a solve function. Okay. But I don't want you to have to memorize, let's say, all the syntax that's involved with how to do something. So all my R programs will be available to you on the course website. But what will not be available to you are my lecture notes or the homework.
So that's going to be like a separate document from the formula sheet?
Yeah. So you go to my section materials on my website. You see all my R programs there. That's what's available. So also it will be to your best interest that you have familiarity. Hopefully you have already been looking at these programs. You have familiarity of where to find stuff in some of these programs. So if I asked you, for example, estimate a regression model. Hopefully you think, oh yeah, that's right. That was in GPA.R. I think it was the LM function. I'm not for sure about the syntax, but I know I can download that program real fast. I have a general idea where in the program that's located, and I can find it if needed.
So we're doing an exam, we have access to that. And will the notes section and the homework sections be taken off for our exam?
I will remove access to the notes and the homework.
So
Our question's going to be, sorry.
Go ahead.
So the data file will be Excel as
A data file. Thank you for bringing that up. I will not put any Excel data files you will not have to use any Excel data files for the test. Okay?
so serious.
It will be like comma delimited or just space delimited. It will not be Excel due to the various problems that we have with Excel files. Is there another question?
Is everything going to be more applied? Will you have things like grouping, say, for example, that standardized and non-standardized correlation?
You might have to do that local.
Okay.
And this is an applied class, but there's very small things like that I would expect you to be able to do.
Anything about plot?
I'm sorry, could you speak up, please?
Anything about plot?
Any about a plot?
Yeah.
Well, for example, it's like a scatter plot. that was done in Introduction to R notes.
Okay, not control.
Excuse me?
No control plot.
Well, yeah, you might have to do a contour plot, but the key thing is that it's going to be hard for you to turn in the electronic version of the contour plot. So in those kinds of situations, there's a few different ways that I can approach it. One, for example, here's an easy one. We can make it multiple choice, where I give you 4 contour plots, and you basically have to do the contour plot yourself in R, and you pick the right one. That's of the 4 that are located there. Or I can say, why don't you sketch on this plot that I have generated that has nothing on it other than maybe some grid lines. Why don't you sketch the f of x equal to 0.01 contour? And based upon you being able to do it in R, you should be able to approximate where it should be located. So that's how I can ask you some questions that involve some kind of graphics or plots. Again, you're using these computers here. TIN is available. RStudio is available. Obviously, R itself is available. If you have not yet, please make sure you can log onto these computers. You know where to find the relevant software packages. During the test, you can have any of those 3 software packages open. You can also have like a web browser open. You can also have like Adobe Acrobat open. But you shouldn't be having, like, say, a Word document open. It wouldn't make sense for you to have that for this test. You should not be, let's say, communicating with others in class via some kind of chat system during the test. So please don't open up any unnecessary windows. One reason why I bring that up is that, obviously, fortunately, it can happen that students will want to cheat. But I can see what's on your screen. There's software on the computer that's located in here, and I can use these monitors here, obviously, then too. I can see exactly what's on your screen. I will be looking at your screens during the exam. You won't be able to tell that I'm looking at your screens, but I will be looking at your screens. So it does not make sense to cheat. Let me just emphasize this again. I can see what's on your screen. The reason why I emphasize that is I have had a student, at least one, maybe 2, students in the past who just didn't get the point when I said that. That student was actually cheating on the exam, and unfortunately he did not do well in my class because of that. Okay, so it's just not worthwhile to do it. Again, you can have access to any of my R programs, the formula sheet. You can use the R help if you want to as well. Obviously, you have access to R, TIN, RStudio, and so on. Please be careful that you don't over-rely on my programs. If it takes you 10 minutes to figure out where did Chris put how to fit a regression model in one of his programs, if it takes you 10 minutes to find out, you didn't study long enough. Okay, so obviously we have some time constraints here, so you need to have a familiarity with where to find necessary information as needed. I mean, that's true in any kind of open book-like tests. That's always the big danger for students is that they didn't study enough and they're, let's say, paging through books, they're paging through the notes trying to find something because they didn't study enough. So again, what's not allowed for you to do with these computers? Again, don't communicate with anybody inside this class or outside this class via the computer. Do not have my lecture notes open on your computer. Do not have my lecture notes open on your computer. Keep your eyes on your own computer screen. So, obviously we have kind of a tiered classroom here. So don't be looking around your monitor to see the person in front of you to see what's on their screen. Also on your own screen, don't be using like a size 50 font so that people behind you could easily see. Okay? Okay, so that's the structure of the tests. Before we do a short review, are there any questions?
Can you bring a printout of your formula sheet yourselves, or is there a pedagogical reason?
I would prefer not to. I don't want you to bring anything other than something to write with.
Some of those are packages
They should be on the computer. I know which packages are on the computers here, and I will not ask you to use a package that's not on the computers. Okay, a real quick review. Sorry again, I went a little bit longer than I had wanted to with today's lecture. So, first of all, we had this introduction to R. You know, some of the basics, such as what is an R function? You know, what do they do? Can you write a very, very, very small R function? How do you use the R help? You know, if you remember in the homework, there was a question where I say, for your favorite probability distributions, go find the corresponding help for it and try to figure out from the help how to find a quantile or a probability associated with it.
So we can use R help in the exam.
Yes, you can use R help in the exam. Sorry if that wasn't clear earlier. Understand what an argument is in an R function call. Essentially, it's like an option. You know, there's required arguments, there's optional arguments. Working with vectors in terms of R's terminology, working with vectors in R. So whenever we use that C function to combine some numbers together, that again was a vector. And we spent some time talking about program editors. I could ask you some kind of small question about program editors. Don't worry if it's not going to be necessary. It would not be necessarily a question that says, how would you do this in Tint? How would you do this in RStudio? I'm not going to ask a question like this, but more of maybe an overall question such as, well, why do we want to use a program editor versus type every line of code line by line inside of the R console window? Then we also had a regression example. You know, this was based upon, you know, your background from a course like Stat 801. But now let's do this stuff with respect to regression analysis in R. So how would you, let's say, read in a data set? So I might actually, let's say, give you a data set on my web page, have you download it during the exam, and estimate a regression model for that data set. How to do a scatter plot. How to estimate a model, a regression model it is. You know, those are all kinds of questions I could ask regarding the regression part. Then we spent a day on matrix algebra. Of course, you know, the very basics, the structure of a matrix. You know, how are things organized inside of the matrix? We spent some time talking about regression and matrix algebra. You know, beta hat equal to x prime x inverse, x prime y, for example. You know, what is a transpose of a matrix? And, you know, what happens if you have a symmetric matrix? What happens then when you take the transpose? Well, it's the same. Then we had matrix addition, subtraction, not too difficult. You know, obviously the multiplication stuff is a little bit harder. I won't ask you to multiply two 10 by 10 matrices by each other on an exam by hand. I could ask you to do that using R. Or I could have you, let's say if I have two 10 by 10 matrices, I could have you set it up. How would you do it by hand? And say maybe do like the one, do the calculation for the 1-1 entry of the resulting matrix, or the 1-2 entry for the resulting matrix. So that helps me understand whether or not you actually understand how matrix algebra is done. I could have you actually do the full calculations by hand for a 2 by 2 matrix times a 2 by 2 matrix. Now, obviously, if I ask you to do that by hand, how could you check your answer? Use R. We're going to go about, I would say a few minutes over. Sorry. Find like the diagonal of a matrix. How is that related to then an identity matrix? Well, all the elements of the diagonal are equal to 1. The inverse of the matrix, and I could have you do a very small, obviously just a 2x2 example by hand. Same with the determinant. And then we talked about eigenvalues and eigenvectors, how to find those. I could ask you again to do a small calculation by hand, but remember you can always check your answer then using the computers. But in those situations too, it's going to be essential for you to actually show me that you understand the process by actually writing out what you're doing. Because if I ask you to do something, let's say by hand, and all you did was give me the final numerical answer, that was it, well, there will be some points taken off because you didn't show me how it was done by hand. Okay, then the last section was this data, distributions, and correlation. Well, what is multivariate data? Oh, it has more than one variable. Okay, good. Then the general structure of multivariate data that we will use in this class, we have this data matrix called X. Make sure you understand the structure of how we put stuff into that data matrix. We spent a lot of time talking about a multivariate normal distribution, or MVN for short. The mean, the covariance matrix, the correlation matrix associated with the multivariate normal. What is f of x as well. Can you work with, do you understand the structure of what f of x looks like in terms of that equation? We did some plotting of the multivariate normal distribution as well. So again, I told you that I could have you, let's say, sketch the f of x equal to 0.01 contour on a blank plot to show me that you understand how to do the plotting. And you could do the plot, using the contour function r first, and then based upon what you see that sketching on the plot. How to simulate data. So I might say, well, why don't you simulate a sample size 20 for me? Calculate the means. It shows me that you understand how to simulate data. We also talked about simple summary statistics. How to find an estimated covariance matrix, for example. How to check multivariate normality for a particular sample. It's not easy. That's what we learned today. And then also standardizing data. Make sure you know what it means, how to use the scale function, for example. Okay, so I know we are over. You're welcome to leave now, but if there's any questions, I'd be happy to answer the questions at this time. And I will keep on recording, too. Are there any questions? Yeah.
Yes. As well to simulate data, when you give a seed, I recall that they have the same.
Yes. Yes, I'll say set the seed right before you run, let's say, the RMPN function. I'll say set the seed right before that, and that will guarantee everyone will get the same sample. Sir.
When you say the structure of the data matrix in the context of multivariate data, do you just mean rows versus columns, variables?
Yep. And the notation associated with it. Okay, if there's any questions between now and Wednesday, please feel free to post them to the lister. I'll be more than happy to answer your questions. Okay, that's it for today.